Okay, so lesson 18. So we're getting into exponential functions now. So you guys haven't really seen a lot of these. In general, here's the form. So it's going to be some number, and then times the base, and then the exponent, right? So this is like just generally how exponents work for us. Let's go through some review though. You guys should be pretty good at these things by now, right? With our product rule, where you would add the exponents, quotient rule, where if you're dividing, you subtract the exponents, power. So if you're doing a power to a power, you'd multiply. Do you guys remember this one? It was a while ago now. If you had a negative exponent, what that means? So if you had like, 3 to the negative 1, what does that really mean? Well, how would you write that out? Yeah.
1 over 3.
Yeah, that'd be 1 over 3. Yeah, so like 3 to the power of negative 2 would be 1 over 3 to the 2. So that negative exponent flips it up or down, right? And then the 0 rule, so anything to the power of 0 is 1, right? Okay, so that being said, this is going to be your guys' equation. This one is on your formula sheet too. You'll probably have this one memorized pretty quick though. Yeah, I guess so. This is another formula. You guys haven't used much yet, but okay. I'll kind of get into this as we go. So yeah, you guys can use these as your notes to look back on to kind of remind yourself. But as we go through the notes, I'll kind of explain, why the A value is the y-intercept and the B is the multiplier and stuff. I won't explain that yet. Okay, just as a little bit of a review here, I'm going to do a couple of these. I won't do all of them. So it says use exponent laws to solve this one. So I shouldn't say solve. We should probably say just like simplify without negative exponents. So, all right. So if I was writing this one out, I think I'd write it as, well, 3's on the top. 5 is still on the bottom, but this x to the negative 3, what's that going to do? Like, where's that going to put that x to the 3? Yeah, in the bottom, right? That's going to flip it down to the bottom. Maybe the same thing as x to the power of 3. Okay, this one might be a little trickier. So I'm going to write this one out again, and really the only issue here is this y to the negative 5 part. So I'm going to just write it out, and when I get to that, we'll see what we can do with that. So this would be 16x squared plus 3. And then what is this going to do? This is going to go y to the negative 5. Is that going to put like y down here? Y to the 5 down at the bottom? You would think so at first glance, but the problem is that this is like a binomial over a binomial, right? So that kind of breaks our rules there. We can't do that, right? So here's what we have to do. We can write just this part of it by itself a little bit different first, though. We can write this as just 3 over y to the 5, right? Just rewriting that part. But then this is still all over 4x to the 4 minus y squared. Okay, so now what I have to do here, if I want to simplify this thing, is I need to have this y to the 5. I need to have this whole thing over y to the 5. Yeah, so what we're going to do there is really kind of like adding fractions here. So I need a common denominator of y to the 5. So what I'm going to have to do here, I'll write this in different colors so you can see it, is I'm just going to write this one as over y to the 5, but then that means I also have to multiply the top here by y to the 5. You guys kind of see what we did?
We can just multiply the 4x4 minus y squared to the top.
Yeah. So then rewriting this, so I'm just ignoring the bottom for a second. Just kind of keep that out of your mind for a second. Now, I'm over a common denominator. So on the top here, I can write the whole thing as over y to the 5. And then on the top, I've just got 16x squared, y to the 5, plus 3. And then that is all over 4x to the 4 minus y squared. Now, when it looks like this, what I like to do sometimes is kind of put brackets around this to kind of, whenever you get a fraction over a fraction, it looks a little confusing sometimes. So it's kind of like we've got that top part over the bottom part. And now the next step here to simplify this is just something over something. Really what we're going to do here, when I'm dividing this, this is really this over 1, right? So what do you do when you divide by a fraction? That's the same as multiplying by the reciprocal, right? So this bottom part I could flip upside down, right? I can multiply that. So this would be the same thing as 16. Oh, yeah, that looked like an, sorry, there should have been x there. It looked like a y. X squared, y to the 5, plus 3. And then that was like y to the 5. And then times 1 over 4x to the 4 minus y squared. So just writing that a little bit differently, we'd write that as 16x squared, y to the 5 plus 3 over, and then on the bottom here now it's just y to the 5 times this, right? So we're just gonna, that's what we're gonna write. So we'll just write it as y to the 5 times 4x to the 4 minus y squared. And then you could expand that y to the 5 into that, but I think we're good enough, eh? Yeah, you guys agree? Okay. Just one thing. So I did all that just to kind of show you what's really happening. But just go back for a second. Do you guys see that at this point, right? You probably could have seen the pattern there, that we could have just thrown this y to the 5 down into the bottom of this one, right? That's what we did in the end. So just look for those patterns, right? That's what ends up happening in the end, is that we put that one down there. But that's the reason why. So, okay. I'm going to skip these two just for time's sake, because we've got a lot to get through. All right. So characteristics of exponential functions. So, you know, the domain, the range, the x-intercepts, the y-intercepts, and end behavior, horizontal and vertical asymptotes. So those things with exponential functions. So here's all your rules. I think for the most part, though, what I'm going to do, let's do some questions, and then these rules I think will make a bit more sense. So we'll graph some things and then see what we get. So here are some examples of exponential functions. Notice that our x value now is up in the exponent, right? That's the difference here. So when we say exponential functions, this is different than before, right? If we had a polynomial function, that was like y is equal to x, you know, cubed or to the 4 or anything like that. That's not an exponential function because there's exponent. An exponential function has our x value up in the exponent. Okay? So let's just think about this first one, how this would look. Y is equal to 2 to the power of x. So let's sketch this one. Okay, so like any other function, we can throw numbers in for x and see what we get out for y, right? So if I threw in y is equal to 2 to the power of, let's say, 0, where would my first point be? 1, right? Because anything to the power of 0 is 1. So I should be crossing my y-axis at 1. Okay, so perfect. Now let's throw another one. So if we had, you know, y is equal to 2 to the power of, and we threw, let's say, 1 in for x, then what are we going to get out for y? 2, right? Yes, because 2 to the power of 1 is 2, so we're going to get 2 there. Let's just do one more just to kind of get the feel for this. So if we threw 2 in, then that would be y is equal to 2 to the power of 2, so y would be 4. So when x is 2, y would be 4. You guys kind of see that like standard like exponential growth that's kind of happening here? The next one's going to go up by like you know, so the next one was 3. That'd be 2 to the power of 3, so that would be 8. Okay? So it's going up and up and up really quick here, right? Let's look on the back end of it though too. What if we threw in y is equal to 2 to the power of, and I threw -1 in for x. So -1.
They would just exponentially get really small because 1 over a bigger denominator is a really smaller number.
Perfect, yeah. Yeah, so if I write this a different way where it makes a bit more sense, 2 to the power of -1, that's the same thing as 1 over 2, right? It's equal to a half. So when x is -1, then y would be a half. And now let's just do one more for good measure here. So if we went y is equal to, let's say, 2 to the power of -2, well, that's the same thing as 1 over 2 to the 2, or 1 over 4. So then that's at a quarter. And then you guys can see the pattern here. The next one would be at an eighth, going down and down and down. Do you guys see how I'm approaching x, right? Like, so as it's getting closer and closer and closer to x. But it's because these numbers, like you were saying there, if I had y is equal to 2 to the power of, let's say, 10, or negative 10, right? I put like x -10 in for that. Well, then that's going to be y is equal to 1 over 2 to the 10. And 2 to the 10 is a really big number, right? So I've got like 1 over a giant number. I'm getting ever so close to 0, right? So that's going to be our horizontal asymptote, is right at the line y is equal to 0. You never quite get there. Does that make sense? Okay. All right, so that's our first one. So I'm going to sketch that. Okay, so that was y is equal to 2x. All right, now the next one. Sorry, I'm kind of sketching all over the place here. Okay, so now let's, hopefully you guys have more room than me now. Let's do the next one. So if we went a half, right? So if I threw in, let's say, so y is equal to 1/2, and then to the power of 1. Okay, where would x be here? So when x is 1, y would be?
1 over 2.
Yeah, it'd be a half, right? So it's going to be right here. Maybe I should have backed up a bit here too. What if I would have had y is equal to 1 over 2 and I threw 0 in for x? Where would that be? Anything to the power of 0 is? 1. Yeah, anything to the power of 0 is 1, right? So right there, right? So it's still going to be at 1. So it's going to cross through 1. Okay.
Same thing as the negative exponent, right?
Yeah. So now let's do one more. If I said like is equal to 1/2 to the power of 2, so I'm in a little out of order here, that'd be the same thing as 1 over 4, right? So then when x is 2, that would be at 1 over 4. So again, I'm approaching that x, but that x-intercept, right? So my horizontal asymptote there. But let's move to the other side now. What if I threw in -1? Well, that would be y is equal to 1/2 to the power of -1. What does that negative do? Yeah, so that -1 is taking the reciprocal, right? So then we flip those. So that would be the same thing as y is equal to 2 over 1, or just 2. So when x is -1, y is 2. So we're up there. And then the same pattern continues, but on the other side.
Will we get ones where like not the x term is negative, like -2 to the power of something? Because that would,
you know what? You're right.
go like,
Yeah, you're right. That's good. That would actually make it look really funny, wouldn't it? We don't typically do a lot of those with like the base being like a negative number, because that does flip it top and bottom. Yeah. But yeah, typically we don't, just because of that. It's not that useful. These ones are really useful. We'll get into like exponential decay and like carbon-14 dating and all that kind of stuff, right? Like these actually have a lot of applications in real life, right? With a negative base, they don't quite have as many real applications. Okay, so y is equal to 1/2 to the power of x. Look like that one, right? Okay, again, for the sake of time, I'm just gonna kind of skip over these next two. They're very similar, but did you guys see in this one that the value of 2 there, that's what's called the multiplier? And that's because, like, you can think our y values, every time they go up, they're being multiplied by 2. So if this one started here, like at 2, then it was at 4, then it was at 8, then it was at 16. So that's our multiplier. It's going up by 2 every time. What do you guys expect with this one, with 10? It's going to go up faster, right? It's going to go up by 10 every time. So you have a multiplier of 10 as you're going exponentially up. So, okay, that's the idea, though. The main thing to take away here is that if your multiplier value, or your, b value, right, in this case, is bigger than 1, then you're going to have exponential growth. And that's going to look like the pink line there going up. If you've got a number between 0 and 1, then you're going to have exponential decay because you're taking like a half, or like in this case, every time, a half of a half of a half of a half, or, you know, an eighth of an eighth of an eighth of an eighth, or whatever it might be, right? Okay, so let's keep going. So yeah, let's do this one. It says, so observe the difference, I should say difference, in the first 2 equations, tables of values, then observe the difference in the last 2 equations, table of values. Okay, so no solution. Oh, that's pretty much what I was just saying there. Sorry, guys. That was that multiplier value every time. Yep. Okay. So sorry, yeah, this one was pretty much the one I was just explaining there. And then, so this one says state the domain, the range, the y-intercept, or x-intercepts, y-intercepts, equation of the asymptotes and end behavior for all 4 graphs. Again, you know, it just, again, for the sake of time, getting through 2 lessons this class, I'm not going to do all that, but let's just kind of talk about it. So the domain, let's say, of the pink graph there, so that one, what would that be? That would be x is a member of the real numbers. This thing does go forever to the left, forever to the right, so it's going to be everything. What about your range for that one?
Greater than 0.
Yeah, it's going to be greater than 0. Not equal to, right? Because it's never going to get to 0. What about your y-intercept on that graph?
1.
Yeah, 1. So it's going to be 1, right? And that's only going to be the case, like we'll see in the next one, when your a value is 1. Okay? But we'll get to that. And then x-intercept? There's not going to be any, right? Because it's approaching that x-axis. All right, next one. So let's graph, yeah, a few of these too. So now we'll do, well, really quickly, let's do y is equal to 5 to the power of x. So if I threw 0 in for that x, that thing would be crossing at 1, right? If I throw 1 in for x, then this thing is crossing at 5. And then this graph, just in general, we know kind of what these look like. It would approach x and then go up through there, right? So this was our y is equal to 5x, or 5 to the power of x. Okay, so now here's the idea. Things are going to change now with this 2 times this 5 to the power of x, because now if I threw a number in there, let's throw 0 in. So y is equal to 2 times 5 to the power of 0. So 5 to the power of 0 is 1 times 2. So where am I at now? So
your a value is always your y-intercept.
exactly, your a value is always going to be your y-intercept. And that's the reason for it, right? So your a value, so y is equal to a times b to the x. Your a value will always be your y-intercept because you're multiplying by 1 at that point. Yeah. Okay, so then let's just throw another number in. So if I threw in 1, then what would that be? That'd be 2 times 5 to the 1, or 2 times 5. So it should be at 10, right? So this thing would be all the way up here. So something like that, just in general. Okay. And then, yeah, that's the main idea. I think we'll cut her short there. Okay. So again, state the domain and the range, x-intercepts, y. Like, I think we'll be okay. Yeah. Let's move through those. Okay, so it says determine an exponential equation in the form of y is equal to a times b to the x, where a is equal to 1. So they told us in this case that this will be equal to 1 for each of the following graphs. So we're given this graph and we need to make an equation out of it. Okay, so in order to have an equation out of it, so if I write down y is equal to a times b to the x, and I know that y is equal to, and then they told us that a is equal to 1 times b to the x, then really all I'm doing here is I'm trying to figure out what b is. Any ideas on how we could solve for this? Just doing stuff we've done in other lessons? Yeah.
Well, actually, I don't know if we've done this in other lessons, but you know the that's what the y-intercept is.
Mm-hmm.
You can, since you know that x.
Like we can do it a bit simpler than that though. I could solve for what b is if I just knew what x and y were, right? Well, it's a good thing they gave us an x and a y, right? That's an x, and that's a y. So let's just throw those in, and we should be able to just figure out what b is from there. So our y value was 27. And then I'm just going to ignore the 1 because it was 1. So yeah, we'll use that point. We could have used this one too. It should work out to be the same. Anyway, so yeah, 27 is equal to, I'm going to leave the 1, so b to the power of, and then 3. So if you guys were going to solve for b in this case, what would you do? Take the cube root. So we'll take the cube root of both sides. Okay, so then b is equal to, what is it equal to? 3, yeah. Okay, so then good to go. Now we just throw it back in the equation. So y is equal to, if you like, 1 times 3 to the power of x, or just y is equal to 3 to the power of x. All right, so we'll do this one quickly. So same thing. I'm just going to write y is equal to b to the x. So then in this case, well, we could use either one again, but I think I like this one better. This point would be, so that'd be my x, that'd be my y. So we're going to have 1 over 25 is equal to b to the power of 2. So then we're going to just square root both sides. So what's the square root of 1 over 25? 1 over 5, right? You just take the square root of the top, take the square root of the bottom. So that's 1 over 5 for b. So then writing it out again, that would be y is equal to 1 over 5 to the power of x. And this makes sense, right? This is an exponential decay graph. It's that standard, with things getting smaller, approaching x on the right.
How would you know that your a is 1?
Yeah, so the question was how, like what, I didn't do that in this one, but you might have to. If it didn't tell you what a was?
Once you find y and b, then we can solve for it.
Yeah, so the problem here though is you'd actually end up with like a 2 equations and 2 unknowns situation, right? So if you were to solve for a there, if you didn't know that it was 1, well, you could set up one situation where it was y is equal to a times b to the x, and you could throw in maybe this point. So that would be 27 is equal to a times b to the x. Sorry, not the x, to the 3. Right, but that's all we know. We don't know how to solve for one of those. But then we could set up another equation where we had 1 over 3 is equal to a times b to the negative 1. And we've got 2 equations and 2 unknowns. So how would you guys solve 2 equations and 2 unknowns? What would be your first step there? Yeah.
Isolate a variable?
Yeah. So we can do it however we want. It might be good, I don't know, maybe this one. We could rewrite this as a is equal to 27 over b to the 3. And then now I could replace a with 27 over b to the 3. So in that case, we'd have 1 over 3 is equal to 27 over b to the 3, and then times b to the negative 1, which is the same as 1 over b. Yeah, okay, so then we'd end up with 1 over 3 is equal to 27 over b to the 4. So b to the 4 is equal to 27 divided by 3. So then the 4th root, oh. Yeah, I did that wrong. So this would be 3 times 27. But yeah, so in the end, we should end up getting 1 if we keep going through that one. But does that kind of make sense? That'd be like a tougher question if you had to solve for both, though. Okay. All right.
How can the 4th root of a number be 1?
Next question here says a filter removes 70% of the impurities from water that passes through it. Multiple filters can be used together to increase the purity of the water. This situation can be represented by a is equal to 0.30 to the power of n, where a is the proportion of the impurities remaining and n is the number of filters used. Okay, so it says, explain why the base of the exponential function is 0.3. So we know that the filter removes 70% of the impurities. So why would this be 0.3 for our multiplier? Right. 0.3 is like how we write 30%, right? So writing it as a decimal. And so this would just be 70%, or sorry, 100% minus 70% is equal to 30%. And then 30% written as a decimal is 0.3. Yeah, so that's just our multiplying factor there. So we're getting 30% of it every time through, right? So graph this function. So if we had on the left side here, I'm going to make this 1. So this would be like everything. So we'll say this is percent as a decimal. Is that what's going to be remaining there? So that'd be 1. This would be 0.5. And then on the bottom, we're going to have number of filters. Or number of times through filter. Okay. So then this could be like, 1, 2, 3, 4. I'll go to 5. Okay, so very first one here. So if we had no filters used at all, right? So 0 filters, what percent of the original would we have left? Yeah, 100 or 1, right? Written as a decimal will just be 1. So our first point is going to be up here. Okay, if we use 1 filter, how much are we going to have? 30%, so that's 0.3. So there. Okay, now 2 filters. So now you might want to go to the equation now. So it would be A is equal to 0.30 to the power of, and then 2 filters would be this, right? So 2. So then A would be equal to, what is that, 0? Yeah, of course it is. 0.09. So that would be right about here. All right, and we get a general idea of how this thing's going to look, right? So then it's going to start approaching. So like 30% of that, 30% of that. It gets closer and closer and closer, but never quite gets there. Now, one thing to mention here, though, are we going to connect the dots on this? How come we're not going to connect the dots? Yeah.
Because the amount of filters must be a whole number.
Right. Yeah, we can't have half of a filter or anything else. It's 1 filter, 2 filters, 3 filters. So in this case, the dots kind of are it. So that you just leave it like that. Okay, and then for C here, it says what are the domain and range for the context of this question. So the domain, we would say, so the domain would be, well, n has to be greater than or equal to 0 filters, right? So it can be greater than or equal because we could have no filters. But then this is what's going to change here, what we're maybe not used to. But I'm going to say where n is a member of, and I'm going to change this instead of like real numbers like we do quite often, as just whole numbers, right? Because it's just not going to be the numbers in between. We can't have like, yeah, yeah, it's a new thing. Okay, so then the range here is going to be y has to be greater than 0 or less than or equal to 1. Do you guys see why it's just greater than 0? Because you're never going to get to 0, right? According to this equation, no matter how many filters you use, you'd still have some very, very, very small number of impurities left over. So you never get to 0 with our y. But it can be equal to 1, right? Our y value could be equal to 1 up at the top, so it's less than or equal to 1.